Our solar system isn't the quiet place we imagined. There are deep mysteries right here, in our own backyard, that don't fit with how we think planets should work. You'll come away seeing it not as a settled map, but as a kind of puzzle box, with 25 big questions still open. There's a world where the sky moves faster than the planet turns. There's a six-sided storm that's lasted for hundreds of years. These aren't just oddities somewhere else. They're clues right in front of us that challenge some basic science. So what's the one cosmic riddle that makes you wonder about our place in all this? Venus has this contradiction. The planet turns so slowly. A single rotation takes 243 Earth days. That's longer than its year, 225 days to go around the Sun. A day is longer than a year, but above that surface, the atmosphere is in a frenzy. Up at the cloud tops, the sky is whipping around the planet, over 200 miles per hour. That's superrotation, a global hurricane that circles Venus in just 4 Earth days. Screaming around 60 times faster than the ground crawls. How can the atmosphere move so violently, so independently from the planet it surrounds? It's like the shell of an egg spinning wildly while the yolk inside stays almost still. The sun's intense heat seems to be the driver, but the mechanics get mysterious. One idea is thermal tides, not like Earth's ocean tides from the moon. These are massive bulges in the atmosphere itself, heated on the day side, cooling on the night side. That constant solar pounding could generate atmospheric waves, transferring energy upward to fuel those high-altitude winds. Another piece is the planet's lack of a strong magnetic field. The solar wind interacts directly with the upper atmosphere, maybe adding another push. But when scientists run their best climate models, they can't quite replicate the ferocity, the perfect persistence of this planetary gale. Something's missing from the equation, some hidden feedback loop, some transfer of energy we don't yet understand. And this isn't just academic. Unlocking Venus's superrotation is a key to understanding planetary climate engines. It forces the question of how atmosphere and surface interact on a global scale, a question that applies to worlds far beyond our own. The Japanese Akatsuki orbiter has been our sentinel at Venus for years. Its cameras and sensors mapping cloud patterns, tracking wind speeds, hunting for the subtle pulses of energy that keep this atmospheric monster alive. Each new data point is a clue. What we learn from this shrouded world might one day help us interpret the weather on distant exoplanets, skies we can only observe from light years away. So we watch and we calculate, trying to solve the riddle of a sky that moves faster than the world beneath it. A reminder that even our closest neighbor operates by rules we're still trying to decode. That atmospheric whirl on Venus is one kind of paradox, but geometry can be a mystery all its own. There's a shape above Saturn's north pole that shouldn't be there. A perfect hexagon, a six-sided jet stream, each side longer than the Earth is wide. It's not a cloud, it's a colossal wave pattern, a rigid structure etched into the fastest winds. The Voyager probes first saw its outline in the 80s, just a faint, puzzling shadow. Then decades later, Cassini arrived and it gave us the view. Its cameras showed a storm of staggering precision, a honeycomb cell on a planetary scale, spinning for what could be centuries. This is where fluid dynamics meets a paradox. In nature, swirling fluids, air, water, they tend to create circles or ovals or chaotic vortices. They don't settle into stable, angular polygons. You can see it in your coffee cup. Stir it, you get a circular whirlpool, not a triangle, but on Saturn, the physics of its deep, churning atmosphere has locked into this six-sided pattern. And it refuses to let go. Scientists have recreated hints of this in labs. By spinning a cylinder of fluid, they can produce polygons, squares, hexagons, even octagons. It requires a very specific balance between the rotation speed and the viscosity, the thickness of the fluid. But scaling that delicate experiment up to the atmosphere of a gas giant, that's a monumental leap. The hexagon's razor-sharp edges, its unwavering stability, they point to something deeper. They hint at unseen processes far below the cloud tops in Saturn's interior. The planet's own rotation, the churning of different layers of metallic hydrogen and helium that may be setting up a standing wave, a wave that propagates all the way up to the visible clouds. It's like a deep planetary hum, a hum that manifests as a geometric tattoo on the North Pole. This isn't just a curiosity, it's a stark reminder. The rules we understand on Earth are just a subset. A subset of a much wider, weirder set of possibilities. Saturn's hexagon is a natural laboratory, a laboratory for physics at an impossible scale. It asks us how order can emerge from chaos, and how a world we've watched for generations can still hold a secret so precise, so mathematical, it feels almost artificial, a shape drawn in the sky, waiting for us to understand the hand that drew it. Saturn's hexagon shows this persistent, geometric order, but then you have a storm that doesn't follow any kind of schedule. Way out at Neptune, in that deep blue twilight, storms appear like ghosts. They're Earth-sized dark vortices, these colossal anticyclones swirling in the ice giant's frigid atmosphere. Voyager 2 saw the first one back in 1989. A great dark spot as big as our own planet, raging in Neptune's southern hemisphere. Then Hubble looked just a few years later and it was gone. Simply vanished, and another one had appeared somewhere else. That's the behavior of an atmosphere we just don't understand. Jupiter's great red spot is an ancient, grinding fixture. Neptune's dark spots are ephemeral. They can bloom into existence, dominate the weather for a handful of Earth years, and then fade away without a clear trace. That transient nature is the core of the mystery. What internal engine suddenly concentrates enough energy to birth a storm that big, only to let it dissolve so quickly? Jupiter and Saturn, they're gas giants. They still glow with leftover heat from their formation. Neptune is an ice giant. It should be colder, quieter. But it has the fastest sustained winds in the solar system, supersonic gusts screaming across its surface, and these mysterious dark spots ride those winds. One leading idea points to Neptune's internal heat flow. It radiates more than twice the energy it gets from the distant sun. That internal warmth from gravitational compression maybe, or the slow sinking of heavier elements. It has to drive the atmosphere's violent convection, so maybe these dark vortices are like massive atmospheric chimneys, towers of upwelling gas that cool and condense into dark clouds of hydrogen sulfide, creating a visible hole in the brighter methane cloud deck. Their disappearance could be tied to wind shear. Neptune's ferocious jet streams might tear the storm apart, dispersing its structure before it can stabilize. Or the vortex might drift toward the equator or a pole where different atmospheric conditions cause it to unravel. Every time Hubble or a ground-based telescope catches a new dark spot, it's a race. Astronomers scramble to measure its wind speeds, track its movement, model its life cycle before it inevitably winks out. Every observation is a snapshot. A snapshot of a process we've never seen from beginning to end. This isn't just about storm prediction. It's a fundamental question about energy and stability. In alien atmospheres, Neptune offers a stark contrast to the enduring storms we see elsewhere. Its chaos teaches us that planetary weather isn't a single phenomenon. It's a spectrum, from the centuries-old hexagon of Saturn to the fleeting ghosts of Neptune. Each world writes its own rules in the sky, and for the ice giants, those rules seem written in vanishing ink. Iapetus is a moon of Saturn, and it looks like a mistake, or maybe it's intentional. One half is white, bright white like snow, the other half is black. Darker than charcoal, a perfect split right down the middle. It's not a shadow, it's the actual surface. One side always faces forward in its orbit, and that side is black. The other side trails behind, and it's white. So the question is how? How does a world end up painted like that? The main idea starts with another moon. Phoebe, a dark outer moon of Saturn, probably captured from somewhere else. It's covered in dark stuff, carbon material, and it gets hit. Small impacts throw up a ring of this dark dust. And Iapetus, moving along, its leading side just collects it, like a windshield. But that's just the start, because then a cycle begins. A dark surface gets warmer. It absorbs sunlight, and Iapetus is made of water ice. So when a dark patch warms up, the ice there sublimates. It turns to vapor and leaves, and it leaves behind the dark material that was mixed in, which makes that spot even darker, which then absorbs more heat, which sublimates more ice. It runs away. The dark areas get extremely dark. The bright areas, they stay cold, so the ice stays. It's a clean idea, but the details don't fit. The line between them is so sharp. It's not a blend, it's a boundary. Why isn't the dark material scattered? Why hasn't it been mixed up by impacts over time? And what is it exactly? Is it really from Phoebe, or could it come from inside Iapetus itself? And why here? Why is this the only place it happened so perfectly? There are other moons with two tones, Hyperion. It's dark and spongy, but nothing like this, nothing with this global split. Iapetus is like a monument. It's a specific balance, an orbit, a dust source, a surface that can sublimate, the right distance from the sun. Change one thing and the effect disappears. So we look at it, this divided moon. It's a natural experiment. It shows how material moves in a system, how a world's color can decide its own climate. It's a signature. Sometimes the universe doesn't just make a world, it signs its name. Iapetus has that stark division on its surface, but some secrets are hidden under the ice. Enceladus is a small, gleaming world, a ball of ice orbiting Saturn. For a long time, it just looked like another frozen marble. Then the Cassini spacecraft saw something impossible. At its south pole, great plumes of water were erupting into space, not lava, cryovolcanoes, geysers of salty water ice, shooting hundreds of miles high from deep cracks. They form a faint, shimmering ring around Saturn. Cassini didn't just see them, it flew right through one. Its instruments tasted the spray. They found simple organic compounds, the chemical building blocks for life. They found silica nanograins, tiny particles that, on Earth, only form in superheated water interacting with rock. The conclusion was staggering. Enceladus isn't just an icy shell. It has a global, liquid water ocean, an ocean trapped between the rocky core and the icy crust. And at the seafloor, there are likely hydrothermal vents, hot springs on an alien ocean floor, rich with chemistry. This is where the mystery deepens. It turns into a profound question. What is the engine? What source of heat could keep a global ocean from freezing on a moon so small and so far from the sun? The primary answer is tidal heating. Saturn's immense gravity squeezes and flexes Enceladus as it orbits. That constant kneading generates internal friction. That friction creates warmth. It's like repeatedly bending a paperclip until it gets hot. But is that enough? Some scientists calculate the tidal forces alone might not account for the power of those plumes. For the likely warmth of that hidden sea, there could be another contributor, radiogenic heat, heat from the slow, natural decay of radioactive elements in the moon's rocky core. That combined energy tidal flexing plus a warm heart might be the formula. It might create the conditions for a circulating, chemically rich ocean, and that shifts everything. It shifts our gaze from surfaces to interiors, from dead rocks to living systems. Enceladus now stands as one of the most promising places in our solar system to look for life beyond Earth. It has liquid water, an energy source, organic chemistry, the right minerals. It has all the ingredients we know are necessary. We don't know if the recipe has been followed. But the kitchen is certainly active. Future missions are already being dreamed of. Probes that could orbit Enceladus or even land at the tiger stripe fractures of its south pole. To sample those plumes more directly, to search for more complex molecules, for signs of biological processes, this tiny moon, once an afterthought, now represents a fundamental possibility. It tells us that life, if it exists out here, might not need a sun. It might thrive in the eternal dark, warmed from within by the gravitational embrace of a giant planet. The plumes of Enceladus are a message written in water vapor and salt, saying that even the smallest, coldest worlds can hold the greatest of secrets. Europa is a different kind of promise. Its surface is a frozen labyrinth, a global jigsaw puzzle of ice with cracks and ridges everywhere, but in certain regions that order breaks down. It becomes chaos terrain, vast areas where the ice crust looks completely shattered, like gigantic icebergs broke apart, tumbled, and then froze again in place. This isn't a dead landscape, it's a dynamic shell, and it floats on top of a global ocean, a salty ocean that might hold twice as much liquid water as all of Earth sees. The driving force is Jupiter's gravity. As Europa orbits, that pull flexes the moon. It creates tidal heating deep inside. That heat keeps the subsurface ocean from freezing. And it probably powers the geological chaos on the surface, but the exact mechanics are a puzzle. How does the heat and material from that hidden sea actually reach the surface? One idea is ice convection. Think of a lava lamp. Blobs of warm wax rise, cool, and sink. On Europa, warmer ice from near the ocean might slowly rise through the shell. As it gets near the frigid surface, it deforms the brittle upper crust. It fractures it. This could create the chaos regions. Blocks of older surface ice break apart. They drift on a slushy layer and then refreeze into new, chaotic patterns. Another possibility is direct contact, where the ice shell is thin, or where tidal stresses crack it all the way through. Ocean water might erupt onto the surface. It would flash freeze in the vacuum of space. That creates new ice, and it deposits whatever minerals are dissolved in the water. This brings us to the color in the cracks. Those reddish-brown streaks lining the fractures, they're contaminants, but from where? They could be salts from the ocean below, magnesium sulfate, or common table salt, sodium chloride, darkened by radiation from Jupiter's magnetic field. Or they could be more complex organic material, compounds that have welled up from the ocean and been altered by the harsh surface radiation. Each scenario tells a different story about the ocean's chemistry. And chemistry is the foundation for biology. This is why understanding Europa's icy tectonics is so critical. It's not just geology, it's a window into the habitability of that dark, global sea. The movement of ice and water is a conveyor belt. It could transport oxidants from the surface down into the ocean. That would provide a vital energy source for any life that might exist there. It's a complete, if alien, ecosystem in theory, an energy source from tidal heat, liquid water, organic chemistry, and a possible mixing mechanism. Europa's fractured face is a map. A map of the forces at work below. Every ridge, every chaos zone is a clue to the processes that connect a hidden, watery world to the sterile surface we can see. Our next missions, like Europa Clipper, are designed to read this map, to measure the thickness of the ice shell, to analyze the composition of those colorful streaks. To search for recent plumes of water vapor, the goal is to understand the engine of this world, to see if its ocean is truly in contact with a rocky, mineral-rich seafloor. Because that contact is where the most interesting chemistry of all could be happening. Europa whispers a possibility. that life might not need a sunlit surface. It might thrive in perpetual darkness under the pressure of an icy sky, warmed only by the rhythmic flexing of a distant giant. Its chaotic terrain is the signature of that hidden power. A cracked and frozen canvas telling a story of a deep, dark, and potentially living sea. Water isn't the only thing that can carve a world. There's another place with rivers and lakes and seas made of something else. Titan, Saturn's biggest moon. It's wrapped in this thick orange haze, a nitrogen atmosphere that's actually denser than Earth's. For a long time, that haze blocked our view. Then the Cassini spacecraft got there. Its radar looked right through the smog, and it showed a landscape that felt familiar but was completely alien. There were shorelines, river deltas, big, dark lakes near the poles, but they weren't water. On Titan, it's about 290 degrees below zero. Water there is just rock. The liquid that flows is hydrocarbons, methane and ethane. They do what water does here. They evaporate, make clouds, rain down, carve channels, fill basins. It's a full weather cycle, but with totally different chemistry, and that creates the first big puzzle, the methane cycle. Sunlight up in the atmosphere is always breaking methane apart. Over geologic time, that should have used up all the methane in the air long ago, but the lakes are still full, the clouds still form, the cycle keeps going. So something has to be adding more methane back. What's the source? One strong idea is a huge reservoir underground, a global ocean of liquid water and ammonia deep under the ice crust. Could be a layer where methane forms from reactions and then seeps up. Another idea is cryovolcanoes, volcanoes that erupt water or slush, which could carry methane from inside up to the surface, where it vents into the air. Cassini saw things that looked like volcanic domes and flows, but we don't have proof it's still active. The methane mystery is really about planetary plumbing. It means we have to understand Titan as a layered world, with things moving between its deep interior, its crust, and its thick sky. The second mystery, maybe deeper, is what this means for chemistry. Titan's atmosphere is like a factory for organic molecules. That sunlight breaking up methane starts a chain of reactions, making a complex soup of hydrocarbons. That's what forms the orange haze particles. They eventually drift down to the surface. It's like a slow, constant drizzle of organic stuff. Over billions of years, that drizzle has probably built up deep layers of organic sediment around the lakes and across the plains. And in those freezing methane lakes, who knows what other chemistry is happening? It presents this radical alternative. On Earth, life's chemistry is based in water. Titan shows us the basic processes of organic chemistry. Building complex molecules can happen in a completely different liquid under totally different conditions. It's a natural lab for probiotic chemistry, a place to study the steps that might lead toward complexity, even life, along a path we've never seen. The Huygens probe gave us one look from the surface. A pebbly ground under a dim, orange sky. Future missions want to go back. A drone rotorcraft could fly from lake to lake, sampling the liquid and the shore. A submarine could one day dive into Kraken Mare, a sea bigger than the Caspian. What would it find? Titan's methane lakes aren't just a curiosity. They show nature's versatility. They prove the processes that shape planet's erosion, weather, liquid cycling aren't unique to Earth. They're universal principles. They just use whatever materials are there. Titan holds up a dark, hydrocarbon mirror to our own world. And in that reflection, we see a universe that's broader and stranger and more creative. Methane isn't just on some far-off moon. We've been picking it up right next door, on Mars. The thin, cold air there sometimes has this faint trace of methane. Our robots have smelled it. The Curiosity rover in Gale Crater caught these sudden, short spikes, and the Trace Gas Orbiter from above has seen broader plumes that come and go with the seasons. It's a detective story told in parts per billion. On Earth, methane is a strong signal. Most of it comes from life, from microbes, from animals, from things breaking down. But there's another way, a geological process, serpentinization. When certain rocks react with water and carbon dioxide underground, they can make methane. No life needed, so which is it on Mars, a sign of something alive or just chemistry from a wetter past? The pattern makes it stranger. The methane isn't constant. It comes in sporadic bursts, sometimes in one spot, sometimes over a wider area. That means a hidden source. Something is producing it or releasing it in pulses, and then it just scatters in that thin air. Maybe there are pockets underground where methane builds up, trapped under ice or rock, until a quake or a pressure change opens a crack for a little while. Or maybe it's being produced actively, right now, by something. That sporadic nature is what drives the search for a mechanism, a cycle of trapping and release we haven't figured out yet. This isn't just a puzzle, it goes right to the core of looking for life elsewhere. If the source is geological, it's still an incredible story. It means there's active water rock chemistry happening under Mars today. A sign the planet isn't completely dead, and that places that could support life might still be down there. But if the source is biological, that changes everything. It would mean life, in some simple form, found a way to hang on, deep in the dark, wet cracks below the surface, a remnant surviving for billions of years since Mars was warmer and wetter. Solving this needs more than just sniffing from afar. Future missions want to bring precision, new rovers with better instruments, made to not just detect methane but to read its isotopic fingerprint. The specific mix of carbon atoms in the methane can hint at where it came from. Life often prefers lighter isotopes. It's a subtle clue, but a strong one. The final goal, of course, is to bring a sample of that Martian air back, or drill down deep and bring back what's underneath, for the most detailed look possible. Until then, every little whiff of methane is a siren call, a whisper from Mars we don't yet know how to hear. It's a reminder that the line between a living world and a dead one can be incredibly thin. Written in a gas we can barely measure, drifting on the cold wind. Mars has these other temporary marks, on slopes that face the sun, on crater walls and canyon sides. When it gets warmer, dark streaks show up. They look like long, dirty fingers stretching downhill. They can grow for weeks, getting longer, sometimes hundreds of feet, and then they fade when the cold comes back. These are the recurring slope Lineae. Orbiters saw this seasonal pattern over 10 years ago, and it caused a lot of excitement right away. The behavior pointed straight to liquid water. It meant that even in Mars's thin, freezing atmosphere, salty water might be trickling just under the surface, darkening the ground as it moved for a short time. The idea of active water on the surface today was a huge deal. It changed how we thought about looking for places life could be, but science doesn't always go straight. Better data came in, especially from orbiters with spectrometers that can identify minerals, and that brought a complication. Those dark streaks don't have the clear signal for liquid water. So the main idea changed to a dry process. It might be a flow of grains. The warming sun makes carbon dioxide frost, or water frost, turn to gas at the top of a slope. That release of gas shakes loose a layer of fine, dark sand and dust, starting a small avalanche. The grains slide down, uncovering darker material below, and that makes the streak. As the season goes on and more frost turns to gas, the flow keeps going and the streak gets longer. It's an elegant, almost simple system, but that might not be everything. The mystery is still in the details, in what exactly starts it. Some research points to hydrated salts, perchlorates, that might still be involved. These salts can pull tiny amounts of water vapor from the air, becoming a damp paste. That little bit of dampness could make grains stick together just enough to get a flow started, a mixed process. not completely wet or completely dry. This debate matters because it shapes our view of Mars now. If the streaks are totally dry, then Mars's surface today is even drier and more still than we wanted. If there's even a trace of brine involved, it means liquid water, however brief and salty, can still appear in some spots. That difference decides where we aim our most sensitive tools and where we might one day look hardest for any microbial life hanging on. Future rovers could go to a recurring slope Lineae site to check the soil right as a streak is growing, to test the dust and look for that sign of wetness. For now, we observe from orbit. These puzzling streaks teach patience and careful reading. They show that the best clues usually have more than one layer. A dark streak on a warm slope isn't just a geology event. It's a question written in the sand, a question about water being there, about the turn of the seasons, and about the last, faint signs of activity on a world that used to be so different. That faint methane we detect on Mars, it's a whisper from the present, but the planet's past that's written in its shape. If you look at a topographic map of Mars, you see a world split in two. The southern hemisphere is ancient highlands, battered, covered in craters, and it towers miles above the average. The north is a vast, smooth basin. A low-lying plain, one of the flattest surfaces in the solar system. That's the hemispheric dichotomy. It's not subtle. It's the most dramatic geological border we have in our neighborhood. And it's the key to the whole story of Mars. The leading idea for how this happened is as violent as it gets. A single, staggering impact. Early on, a protoplanet maybe the size of our moon could have slammed into the northern third of Mars. The energy would have been unimaginable. It would have melted the crust, excavated a basin thousands of miles wide, left a permanent scar. That event, called the Borealis impact, would explain the smoothness. Over time, lava flows from later volcanism could have filled the basin, created those flat plains. It would also explain the planet's lopsided nature, its strange gravitational field. But a single impact on that scale, it's hard to prove. There's an alternative theory. It looks inward. It suggests internal processes. A lopsided churning in the Martian mantle could have thinned the crust in the north all on its own. This mantle convection would have stretched and pulled the northern crust apart, made it lower and thinner, while the southern crust stayed thick and high. A third idea involves not one giant impact but a whole barrage. A late heavy bombardment that preferentially battered the south, left the north relatively unscathed to be resurfaced later. The mystery isn't just which one is right. It's about the sequence, which came first, the crustal thinning or the impacts. Did the internal structure make Mars vulnerable to a specific kind of damage? This dichotomy set the stage for everything that followed. It dictated where volcanoes would rise. The vast Tharsis Bulge with Olympus Mons, it sits right on the border between the highlands and the lowlands. It guided where water would flow. Most of the channels carved by ancient floods, they drain from the southern highlands down into the northern basin, suggesting it may have once held a vast ocean. Most profoundly, this early trauma might be linked to the death of Mars's global magnetic field. A giant impact could have disrupted the planet's internal dynamo, the churning of its molten core that generates a protective magnetic shield. Without that shield, the solar wind began stripping away the Martian atmosphere. That loss turned a potentially warm, wet world into the cold, dry desert we see. So this two-faced nature, it's not just a surface feature, it's the foundational event, the scar that decided Mars's fate. Understanding exactly how it formed is like finding the first chapter of a lost book. It tells us why the north is smooth and the south is scarred, why the volcanoes are where they are, why the water went where it did, and ultimately, why a world that started with so many of the same ingredients as Earth took such a devastatingly different path. Every rover we send, every orbital survey, it's collecting clues to read that first chapter. to understand the blow that may have shaped and perhaps even doomed a world. Mars had its shape changed by ancient violence, but Venus, its whole story comes from something missing. Venus is almost the same size as Earth, made of similar stuff. But it doesn't have a global magnetic field, no shield, nothing to push back the solar wind. That missing piece matters. It means the atmosphere is just exposed. The solar wind hits it directly, and over billions of years it strips away the light atoms, hydrogen and oxygen. That stripping is a big part of the puzzle. Part of how Venus turned into this hot, pressurized greenhouse. So why no magnetic field? The main answer is its rotation, or really, the lack of rotation. A planet's magnetic dynamo is like a generator in its core. It needs three things: a fluid that conducts electricity, like Earth's liquid iron outer core; convection, that churning from heat rising and cooler materials sinking; and rotation. The spin organizes the churning into a planet-wide field. Venus fails on the third part. Its day is 243 Earth days long. It spins so slowly that, in our models, it can't stir the core into that organized dynamo action. It's like trying to spin a tire with just a nudge. There isn't enough rotational energy to get it going, but the mystery goes deeper than a slow spin. We have to ask about the core itself. Can it even convect anymore? On Earth, the inner core is solid iron, growing as the planet cools. The outer core stays liquid, and the temperature difference drives the convection. On Venus, it's unclear. The surface shows signs of global resurfacing, huge lava flows that wiped old craters away. That points to a lot of internal heat. But where is that heat? One idea is that Venus's core is completely solid. A ball of iron, no liquid outer layer to churn. Without that fluid motion, there's no dynamo, no matter the rotation. Another idea is the core is partly molten, but not convecting well. Maybe it's too hot, with too small a temperature difference to drive strong currents. Or it could be layered, stratified, so it doesn't mix. We just don't know the internal structure, and this isn't just geology, it's about planetary fate. A magnetic field is a shield. It deflects the solar wind, protects the atmosphere from being stripped away. Without it, Venus was vulnerable. Scientists think early Venus might have had a lot of water. Maybe even oceans, but with no magnetic protection, the solar wind and intense UV radiation broke apart water molecules in the upper atmosphere. The light hydrogen escaped to space. The oxygen stayed behind, binding to rocks or other gases. That process, atmospheric escape, helped drive Venus out. With no water to absorb carbon dioxide and lock it into rock, like on Earth, the carbon dioxide built up. That led to a runaway greenhouse effect. The planet trapped more and more heat, boiled away any remaining surface water, and became the inferno we see. Venus is a powerful contrast, a cautionary tale written in atmospheric chemistry and a missing magnetic field. It shows how two worlds, starting so similar, can split onto totally different paths. Rotation speed, internal heat flow, the presence of water. Understanding Venus's silent core is more than physics. It's a key to reading the history of rocky planets everywhere. It asks what makes a world habitable and what breaks it. Future missions like Veritas and Da Vinci aim to look beneath the clouds, to map the gravity field in detail, which tells us about the interior. To measure the atmosphere's composition for clues about ancient water. Each new piece of data helps answer the central question: is Venus's core still stirring faintly, or is it a still, solid heart? The answer defines not just the planet's present, but explains the hellish turn its past took. A reminder that sometimes what a world lacks tells you as much as what it has. Mercury has this ghost, a kind of shroud around it, not an atmosphere, but an exosphere. A thin collection of atoms just clinging to the surface, and from that there's a tail. A long, faint tail that streams away from the sun, but it's lopsided. This tail, it's made of sodium mostly, and it glows. It stretches for millions of kilometers. And one side of it is always brighter. The tail comes from violence. There's no air to stop anything. Solar radiation hits the surface. Micrometeoroids, tiny particles, they act like a sandblaster. They knock atoms right off the ground. Those atoms get energized by the sunlight, and then the radiation pressure pushes them. They form this long tail pointing away from the sun. Like a comet, but the lopsidedness, why one side is brighter. The magnetic field is a suspect. Mercury's magnetic field is offset. It's not centered on the planet. The north and south magnetic poles aren't opposite each other, so the shield is uneven. On the side where the field is weaker, the solar wind can get closer. It can blast more sodium off the surface into the tail. On the stronger side, the field might deflect the wind, create a calmer area, a fainter flow. Or it could be the ground itself. The surface isn't the same everywhere. There might be patches that have more sodium in the minerals. When the sun hits those patches, or when micrometeoroids strike them, they could release a stronger local puff of material. That would make one side of the tail glow more, or it could be the interaction with the sun. The solar wind carries the sun's magnetic field. Those field lines wrap around Mercury. They can connect with the planet's own field in a process, magnetic reconnection, that can open temporary windows in the planetary shield, funnel the solar wind to specific areas. Enhance the sputtering on just one side. The Messenger spacecraft mapped this. It showed the tail's structure changing, pulsing with the solar cycle. It's not a static thing, it's dynamic, a weather vane for the sun's mood. Studying this tail, it's about more than Mercury. It's a masterclass in a process that happens all over. On our moon, on asteroids, on other airless bodies, atoms are constantly being knocked into space by these same forces. Mercury just makes it visible. On a grand scale, it's a clean laboratory for understanding how a world's soil talks to the space around it. The tail is a signature written in sodium light. A signature of bombardment, of magnetic fields, and of a surface slowly, almost imperceptibly, evaporating into the void. It's a reminder. Even a world without air has an atmosphere of sorts. A whisper of itself, stretching out into the dark, telling a story of perpetual loss and a delicate balance. Uranus looks like it fell over. Most planets spin upright like tops. Uranus rolls, it rotates almost on its side. The axial tilt is 98 degrees. That gives it the most extreme seasons in the solar system. Picture this. One pole faces the sun for 42 Earth years, a single day that lasts for decades. The opposite hemisphere is in total darkness for 42 years. A deep, long night. Then, over its 84-year orbit, the roles slowly swap. The planet doesn't have seasons. It has two alternating extremes. How does a world end up like that? The leading story is ancient chaos. Early in the solar system, a protoplanet the size of Earth is thought to have slammed into Uranus, a glancing blow. So colossal it knocked the young planet onto its side. That one event would explain the tilt, but the mystery deepens when you look at its entourage. Such a violent impact should have left a mark. The orbits of its moons and rings should show that trauma, yet they orbit neatly around the planet's new, tilted equator. They seem to have formed after the tipping or realigned. This suggests a more complex history. Maybe the impact was so early that the moons and rings we see are a second generation, formed from the debris, or maybe the story isn't an impact at all. Another idea points to gravitational resonances during the solar system's turbulent youth. As the giant planets migrated, shifting positions, Uranus could have been caught in a tug of war with Jupiter and Saturn, a prolonged dance of forces. That might have gradually pulled the planet over, a slow cosmic tipping. This orientation isn't just a curious fact, it rewrites the planet's entire physics. With the poles alternately facing the Sun for decades, the internal heat flow is scrambled. Unlike Neptune, which glows with internal warmth, Uranus is curiously cold. It emits very little heat of its own. Did that giant impact drain its internal energy, or the gravitational struggle? The tilted rotation also complicates its magnetic field. It's oddly offset and tangled, and this orientation dictates its weather. During the solstices, one pole bakes in permanent sunlight. The equator lies in perpetual twilight. That should create temperature imbalances, drive monumental storms, yet when Voyager 2 flew by during its southern summer, the planet appeared as a nearly featureless blue-green ball. Recent observations from Earth have shown something else. As seasons change, Uranus's atmosphere does erupt with giant storms. It's a climate system operating on a timescale we can barely observe. A single human lifetime isn't long enough to watch a full Uranian season unfold. We have only snapshots, pieces of a puzzle that spans centuries. This sideways world is a monument to the violence and strange dances that built our solar system. It asks us to consider not just how planets form, but how they can be completely rearranged. Uranus is a lesson in celestial imbalance, a reminder that a planet's history is often written in its tilt. Jupiter's rings are faint, Saturn's rings are bright, made of ice. Jupiter's are different, they're made of dust, very fine dust, so faint we only saw them when Voyager looked back at Jupiter with the Sun behind it. It's not ice reflecting light, it's a haze, dark particles smaller than smoke forming a thin disk around the planet. That faintness tells you something. They're not permanent, they're temporary, they have to be renewed constantly, and the renewal comes from Jupiter's small, close moons, moons like Metis. Adrastea, they orbit inside Jupiter's radiation belts. They're the source. The mechanism is a kind of rain. Micrometeoroids, tiny specks moving fast, hit these moons. When they hit, they kick up dust from the moon's surface. The gravity on these moons is weak, so that dust escapes. It goes into orbit around Jupiter. It joins the ring, but it's not that simple. The dust doesn't spread out evenly. It forms structures. There's a faint inner halo puffed up above and below the equator, and a broader, more diffuse gossamer ring farther out. So how does impact dust form these shapes? Invisible forces. Jupiter's magnetic field charges the dust grains, affecting their motion. The gravity of the supplier moons herds the dust, keeps it in certain zones, and sunlight itself, the pressure of light, gives a gentle push. It slowly changes the orbits of these particles over time. So it's a flowing system. A dust grain gets launched from Metis. It enters the ring. It spirals slowly because of light pressure. It might eventually hit another moon or fall into Jupiter. Its lifetime is short. That means the rings we see are just a snapshot of a process happening right now, creation and destruction. Studying these rings is like listening to a quiet conversation. Between the moons, the dust, and the giant planet's forces, it shows that ring systems aren't just ornaments. They're active, they evolve. The same processes that sustain Jupiter's dust rings are at work at Saturn. And at Uranus and Neptune, they just have different materials. Understanding the faintest system gives you a key to understanding them all. It reveals a kind of heartbeat. The constant rain of impacts, the slow dance of dust, the subtle forces that sculpt emptiness into something fragile, something that has a form. Saturn's rings are mostly faint, almost like a whisper, but one ring isn't like that. The F ring is a shout. It's a narrow band just outside the main rings, and it's alive. It twists and knots. It grows these streamers that come and go. It's not a static thing, it's a performance, and the directors are two tiny moons, Prometheus and Pandora. They orbit on either side of the ring, herding its particles, keeping it sharp. They're shepherds, but their herding isn't gentle. Prometheus, the inner one, is the main actor. Its orbit is slightly elliptical, So each time it comes around, its closest approach changes. Sometimes it dips right into the ring's inner edge. Its gravity pulls a stream of icy particles out with it. It carves a channel, a dark gash in the ring. Then, as Prometheus moves on, that channel gets stretched. It becomes a long, bright streamer, a cosmic signature. It lasts until the next pass. Pandora, on the outer side, exerts its own pull, often in opposition. The ring material is caught in this constant tug of war. Between these two gravitational influences, the result is a ring that looks different every time. Braids form where gravitational resonances pile particles up. Kinks and knots appear from clumps within the ring itself, maybe temporary aggregations held together by their own weak gravity. The Cassini spacecraft watched this for over a decade. It saw Prometheus steal material, then have it pulled back by Pandora. It saw new structures born in a single orbit. This is the mystery in motion. We understand the forces. Gravity, orbital resonance, collisions, but the system is so sensitive, so dynamically chaotic. Its exact state is unpredictable. It's a real-time laboratory. For processes that shaped the entire solar system, the shepherding, the accretion into clumps, the disruptive pulls, this is how planets may have formed from the protoplanetary disk. But here, it's happening on a small scale, an observable scale, and it's happening fast. The F-ring challenges our desire for order. It shows that even under the clear rules of gravity, the outcome can be complex. Beautifully, endlessly complex. It's a lesson in celestial choreography, where the dancers keep improvising, a narrow band of ice and dust forever being written and rewritten. By its tiny, restless guardians, deep grooves around the equator of Vesta, they're not random. They're a system of parallel trenches, some hundreds of miles long, miles deep, wrapping the world like lines on a fossilized melon. This is a protoplanet surface, a world that almost became a planet, and these grooves are scars from a trauma that almost broke it. Vesta is the second largest thing in the asteroid belt. And it's layered. It has a core, a mantle, a crust, a differentiated body like Earth or Mars. That structure is the key, because when something massive hits a layered world, the whole globe can ring like a bell. The theory points to two colossal impacts billions of years ago. They made the giant basins, Resilvia and Venonea, impact craters on a staggering scale, one at the South Pole, the other overlapping it. The force sent seismic shockwaves through Vesta's entire body. The energy had to go somewhere. It focused around the equator, the planetoid's weakest structural point. The global stress caused the crust to fracture, a series of massive parallel faults. The ground split open along lines of least resistance, creating those deep troughs. Like striking a glass globe twice with a hammer and watching cracks propagate around its middle. But the precise mechanics are a puzzle. Why did the fractures align so symmetrically? Why at the equator and not a more chaotic pattern? Computer models try to simulate it. They input Vesta's internal structure, the impactor's angle and speed, how seismic energy moves through different materials. The goal is to recreate that perfect equatorial cracking. It's a forensic exercise. Each model that fails tells us something new about the strength of Vesta's crust or the nature of those ancient impactors. The grooves are a recording of extreme violence from the solar system's youth. Solving this is more than one asteroid. It helps us read the surfaces of other battered worlds. Mercury has its giant lobate scarps, cliffs from cooling and contraction. Mars has Valles Marineris, that vast canyon system. Could some of these features also be from global-scale shock? From ancient impacts, Vesta offers a pristine example, a world where cause and effect are still clearly written in the rock. By studying its grooves, we learn to interpret the cryptic scars on planets and moons. We learn how celestial bodies absorb and display the memory of immense force. Vesta's lined face is a testament to a time when the asteroid belt wasn't a quiet place of drifting rocks. It was a chaotic construction zone where worlds collided and fractured and left their history etched in stone. Vesta's scars show an ancient force, but other objects in the solar system are spinning their own stories. Asteroids and comets shouldn't spin too fast. Their own centrifugal force would overcome their weak gravity. They'd just fly apart, but we see them, small, rocky bodies tumbling end over end. Periods of just hours, sometimes minutes, rotating so fast that by our calculations they should be torn to pieces, but they aren't. It's a puzzle of cohesion. What invisible glue holds these speeding worlds together? Then the visitor Oumuamua sharpened the mystery. In 2017, this first known interstellar object tumbled through our system. Its elongated shape, its slight acceleration away from the Sun, sparked debate, but from a solar system perspective, its motion raised a basic question. How do small, fragile objects achieve and survive such extreme rotation? For Oumuamua, one leading idea was asymmetric outgassing. Sunlight warmed its surface. Maybe pockets of frozen gas sublimated, jetting out like tiny thrusters. If those jets were off-center, they could have given it a spin, a gentle, persistent push that set it tumbling. We see this in our own comets. As they approach the Sun and heat up, their jets of gas and dust act as natural rocket engines. They alter rotation over time. But there's another, more subtle force at work on countless asteroids, the Yorp effect. The acronym stands for something complex, but the principle is elegant. Sunlight itself can make an asteroid spin. Photons hit an irregularly shaped asteroid. They don't bounce off evenly. The lumpy surface, the craters and ridges, absorb and re-radiate heat unevenly. That creates a tiny, imbalanced thrust. Over millions of years, this minuscule force, this photon pressure, acts like a constant, gentle hand on a child's top. It can slowly speed up an asteroid's rotation, or slow it down. It can even alter its axis of spin. The Yorp effect works with unimaginable slowness. It reshapes the dynamics of small worlds. Then there's the violence of collisions. A direct hit from another rock can impart a sudden, tremendous spin. But that would likely shatter a small body, not leave it intact and whirling. More likely are glancing blows, or the cumulative effect of many smaller impacts over eons. Each one adds a little angular momentum, like tapping a ball to make it spin faster and faster. So we have these mechanisms, outgassing, Yorp, collisions. Yet when we apply our models, they don't always match what we observe. Some asteroids are spinning faster than these processes should allow. That forces a question about their internal structure. Maybe they're not piles of loose rubble, as many are thought to be. Maybe they're monolithic rocks, held together by the intrinsic strength of the material itself. A solid chunk of iron and stone can spin much faster than a bag of gravel before it breaks apart. Or maybe the rubble piles are bound by a weak, cohesive force. Van der Waals forces, electrostatic attraction between fine grains, a kind of static cling on a planetary scale. Every fast-spinning asteroid is a natural experiment. It tests our understanding of strength and cohesion, the long-term effects of sunlight. By studying their rotations, we learn about their composition and history without ever touching them. This knowledge is practical, too. If we ever need to deflect an asteroid, understanding how it's held together, whether it's a solid mass or a fragile aggregate, will be the difference between a nudge and a catastrophic disintegration. These whirling worlds remind us that even the smallest, simplest objects harbor dynamic secrets. They're not inert stones. They're active participants in a slow dance of forces. Spinning tales written in motion and time. The asteroids spin, and that tells you something about the forces in the system, but at the edge, that story just stops. There's the Kuiper Belt, this huge ring of icy material past Neptune, and it has a boundary that doesn't make sense. It has a cliff. For billions of miles, the number of large icy objects stays pretty constant. Then, at about 50 astronomical units out, that's about twice as far as Neptune, their numbers just fall off. It's not a gradual fade, it's a sharp drop. A real cliff out in space. This Kuiper Belt cliff is a border defined by what's missing, and its existence, it goes directly against what our formation models say. The original disk of gas and dust that made the planets should have thinned out slowly with distance. The Kuiper Belt should do the same, so why does it look like there's a fence out there? One strong idea is that there's an unseen architect, the gravitational pull of a hidden planet. That's the Planet 9 hypothesis. A world several times Earth's mass, orbiting far past the cliff, could be herding the distant Kuiper Belt. Its gravity might have cleared out a region, throwing objects inward toward the sun or kicking them out completely, leaving that stark emptiness beyond 50O. The orbital paths of some extreme, detached objects add to this. Their clustered orbits point to a common, massive disturber, but we haven't seen it. Another idea looks back to the start. It says our sun's birth cluster wasn't quiet. A passing star in that crowded early space could have come very close. Its gravity would have worked like a cosmic scythe, stripping away the outer disk of material and cutting that sharp edge we see now. The solar system's backyard would have been trimmed by a visiting star. Or maybe the disk itself was just cut off. The protoplanetary disk everything formed from might have had a finite, sharp outer edge. Maybe the cloud that collapsed to make our sun was only so big, or maybe processes inside the disk, like pressure fronts or magnetic fields, stopped material from spreading further. The Kuiper Belt objects then formed only inside that preset zone, creating a natural boundary. Each explanation shows a different picture of the system's early life. A hidden planet means an active, ongoing shaping. A stellar flyby means a single, dramatic galactic event. A truncated disk suggests a quieter, more contained beginning. To solve this, you have to look at what isn't there. It means surveying the darkest, most distant areas with more powerful telescopes, searching not just for the missing objects, but for the reason they're missing. This cliff isn't just a statistical oddity. It's a fossilized edge, a line drawn in the frozen dark that holds a record of forces we can't see anymore. Whether it marks the territory of a hidden world or the ghostly pass of a sibling star, it tells us the story of our solar system's formation isn't finished. The last chapters might still be written in ice and shadow at the very frontier of the sun's reach. Our planet is this blue marble in the black, a world of oceans. But where all that water came from, that's a mystery we carry inside us. Every drop you drink, every wave, it's a relic, a delivery from the solar system's violent beginning. The classic story is the late veneer. Earth forms its fiery, the surface cools, then a rain comes, asteroids, comets, they bombard the young world. And these weren't just rocks, they were cosmic water balloons full of ice, hydrated minerals. They brought the oceans, they gift-wrapped the planet in its defining feature. It's a clean idea, elegant, but the chemistry tells a more complicated story. Scientists can read a fingerprint in water, the ratio of hydrogen atoms, the isotopes. Water from different places in the solar system has a distinct signature, so you compare Earth's water to water from most comets, the ones from the distant Oort cloud. The signatures don't match. Comet water is heavier, enriched with a heavier hydrogen. If comets were the main delivery, our oceans should share that signature. They don't. That points the investigation somewhere else, to asteroids, specifically a type, carbonaceous chondrites, these primitive, dark rocks from the outer asteroid belt. They have water locked in their minerals, and their hydrogen isotope signature is a much closer match to Earth's, so maybe it was asteroids, not comets. The primary water carriers, but there's another possibility, a more profound one. What if Earth was born wet? The planetesimals that collided to form the early Earth, they might have already contained water. Trapped inside their rocky structures, even in the hot inner solar system where Earth formed, certain minerals can hold onto water molecules through the heat of accretion. This primordial water, baked into the very bricks of the planet, could have outgassed over eons through volcanic activity, slowly filling the basins. So the mystery isn't a simple either-or, it's a cosmic recipe. How much water came from local ingredients baked into the planet itself? How much was delivered later by asteroids from the cooler outer belt? And did comets, despite the mismatch, still contribute a small, vital fraction? Untangling this mix, it's a direct line to understanding our existence. Water is the universal solvent for life. If Earth got its water mainly from local materials, that suggests something, that rocky planets in the habitable zone might commonly have water from the start. If it required a precise bombardment from the asteroid belt, then the conditions for a watery world become rarer, more dependent on a delicate series of celestial billiard shots. In a young planetary system, every time a probe analyzes an asteroid, Hayabusa 2's visit to Ryugu, OSIRISREX's mission to Bennu, it's collecting data for this ancient ledger. We're weighing the primordial against the delivered. The answer changes how we look at every distant, rocky exoplanet. It asks whether a blue sky and a rolling ocean are cosmic defaults. Or the most spectacularly lucky inheritance, the water in our glass is a message in a bottle, a message from a time of fire and collision, holding the secret of how a barren rock became a living world. The water we have now came during a time of chaos, when the sky was full of fire. This was about 4 billion years ago, after the planets had already formed. Then there was a sudden storm of impacts across the inner solar system. That's the late heavy bombardment. You can see the evidence best on the Moon. Those dark plains, the Maria, they're seas of frozen lava that came up from those huge impacts. Earth is bigger, more active, so most of those old scars are gone. Erosion, plate tectonics, but the Moon kept the record. For decades, scientists dated rocks from the Apollo missions, the ages all clustered around that same time. A spike, a lunar cataclysm, a short, brutal period where things just kept hitting. But why then? The planets were already there. The main answer comes from a model of the early system, the NICE model. It says the giant planets Jupiter, Saturn, Uranus, Neptune, they didn't form where they are now. They started in tighter, closer orbits. Over time, gravity from the leftover disk of planetesimals made them migrate. Jupiter moved in a little. Saturn, Uranus, Neptune moved outward. That planetary shuffle was the trigger. As the giants moved, their changing gravity acted like a paddle. It stirred up all the leftover material. The asteroid belt got unstable, throwing rocks inward. The primordial Kuiper Belt was scattered, sending a hail of icy comets toward the Sun. So Mercury, Venus, Earth, Mars, they were caught in a shooting gallery. The mystery now is in the details. Was it one sharp cataclysm, just 100 million years? Or was it a longer epoch with more impact spread out? New looks at the lunar samples suggest it's more complex. Some craters might be older. The spike might have been less intense. Maybe there were multiple pulses of violence. Every new lunar meteorite found on Earth, every new crater count, it refines the timeline. We're detectives at a crime scene 4 billion years old. The implications are deep. It shaped the geology of the rocky planets. It resurfaced the Moon. It might have stripped an early atmosphere from Mars, and for Earth, it's tied to the origin of life. This period of heavy bombardment was both a destroyer and a creator. The impacts were immensely destructive. They sterilized the surface over and over. But they also delivered things, volatile materials, water, organic compounds, the ingredients for life. Some theories say the heat from impacts could have made temporary hydrothermal systems. Warm little ponds where the first chemistry could start. The late heavy bombardment was a cosmic trial by fire, a violent transition between the planets forming and a stable, habitable environment. It makes you wonder how common that kind of turbulent adolescence is for other systems, and it reminds you our peaceful blue world was forged in an age of violence. A necessary storm that may have set the stage for everything after. The Sun has a lithium problem. Our models say a star like it should have a certain amount of lithium in its outer layers. But when we look at the sunlight, we measure far less, and it's not just our Sun. We see this in other Sun-like stars too. Lithium is one of the lightest elements from the Big Bang. And it seems to be missing. The puzzle is in the physics. Lithium is fragile. Inside a star at about 2.5 million degrees, it gets destroyed. It fuses, but that's deep in the interior. The surface where we measure the light is much cooler. The churning convection zone, the layer that brings heat up, shouldn't mix material down that far. So the surface lithium should be safe, preserved, but it's not. Something is carrying that surface lithium down into the hot interior where it burns away. The question is what? One candidate is rotation. The Sun spins. That creates currents, shear between layers moving at different speeds. This rotation-induced mixing could be like a slow, steady stir, pulling surface material deeper over millions of years. Another possibility is magnetic activity. The tangled fields that make sunspots and flares might also drive subtle mixing below the surface, creating pathways for material to sink. There's a more exotic idea too: internal gravity waves, not ocean waves but oscillations in the Sun's plasma, generated by turbulence at the edge of the convection zone. These waves could transport lithium atoms inward. The challenge is these processes are hard to observe, hard to model precisely. Our understanding of stellar interiors comes from theory, from subtle fingerprints in starlight. Each new observation of other stars, each refined solar model, tests these ideas. Solving this is more than accounting for one element. It's about calibrating how stars work, how they mix their ingredients over time. If we don't understand the mixing in our own star, our closest example, then our models for billions of other stars have a gap. This missing lithium connects the Sun's daily reality to the universe's ancient past. It's a clue in the spectrum of sunlight, pointing to a hidden dynamism beneath the stable surface. A gentle, constant process. Over 4.5 billion years, it has quietly erased a primordial element from view. The Sun's missing lithium, that's one clue about what's happening inside. But there's something else, something you can actually see. During a total eclipse, when the moon covers the Sun's face, you see this halo, the corona. A white glow with streamers going out for millions of miles. That light comes from plasma. Plasma heated to over 1 million degrees, and just below it, the Sun's visible surface, the photosphere, is only about 5,500 degrees. So the atmosphere is hundreds of times hotter than the surface. It's like moving away from a fire and the air gets hotter. That's the coronal heating problem. It goes against the basic idea that heat flows from hot to cold. The heat source isn't a mystery, it's the Sun's magnetic field. Those loops and tangles in solar images, they carry huge energy. But how that magnetic energy turns into such intense heat, that's still an open question. One strong idea is nanoflares. Think of the Sun's surface not as smooth but like boiling water. Countless tiny magnetic loops are always emerging, crossing, and reconnecting. Each reconnection is a tiny explosion, a nanoflare. Individually, they're too small to see. But together, a constant rain of these could provide the steady heat for the corona. Another idea is wave heating. The Sun's churning like a pot boiling generates waves. Acoustic waves, magnetic waves, they travel up from the surface carrying energy. When they reach the thinner corona, they can break like waves on a shore and dump that energy as heat. A constant rhythmic pounding that could keep the atmosphere hot. Then there's large-scale magnetic reconnection. This is what drives solar flares and coronal mass ejections. When field lines of opposite polarity get forced together, they snap and reconnect. That releases colossal energy, heating plasma to tens of millions of degrees. Big events are sporadic, but smaller versions might be happening all the time, adding to the background heat. The answer is probably a mix of these. Different processes might dominate in different parts of the corona or at different times in the solar cycle. And untangling this matters. The corona is where the solar wind is born. That stream of charged particles blows past Earth, shapes our magnetosphere, creates auroras, and can disrupt satellites and power grids. So understanding coronal heating is key to predicting space weather. This puzzle also goes beyond our sun. Every star like ours has a corona. Solving it here gives us a universal principle, a way to understand the light and activity of countless other stars. Missions like the Parker Solar Probe, flying through the corona, and Solar Orbiter, observing from a distance, are gathering data, measuring magnetic fields, sampling particles, watching waves. Each finding gets us closer to answering a question that's lasted generations. How does a star heat its own atmosphere to such impossible temperatures? The answer is in the sun's magnetic tapestry, a dynamic puzzle, and its solution tells us about the nature of stellar fire itself. Even the simplest journey can show you something you didn't expect. Pioneer 10 and 11, after their last planetary flybys, they just became these silent ships heading out. But as they drifted into deep space, something was off. Their radio signals tracking them showed this tiny, constant slowing down, a force, an anomaly pulling them back toward the sun. It was incredibly small, less than a billionth of Earth's gravity. But it was there, and for years nobody could explain it. This Pioneer anomaly turned into a quiet obsession. Was it new physics, a local effect of dark matter? Or maybe just a flaw in how we understood gravity? The implications were huge, all hidden in a discrepancy smaller than the pressure of sunlight itself. The answer, when it came, was really a lesson in engineering humility. It was the spacecraft. Their radioactive power sources gave off heat, and that heat radiated away. But it didn't radiate perfectly evenly. There was a tiny anisotropy, a slight preference in direction. More photons bounced off the back of the spacecraft's dish antenna than off the front. And that created a minuscule thrust, a photon recoil pushing back toward the sun. It was the spacecraft's own warmth acting like a faint braking engine. When they finally modeled this thermal recoil, accounted for it, most of the anomaly just vanished. What was left fit within the margin of error? So the mystery came from an unaccounted for whisper of infrared light. But its legacy is still immense. It shows a critical truth about exploration. To find something truly new, you first have to understand your own instrument with impossible precision. The Pioneers weren't just probes. They became the most sensitive accelerometers we ever sent out, detecting a force their own designers hadn't fully calculated. This resolved enigma is a kind of promise. It says the next big discovery in physics might not need a massive collider. It might come from tracking a silent craft in the void. It reminds you the universe often speaks in infinitesimals, a drift of a millimeter per second each day over decades across billions of miles that can point to a truth we overlooked right in our own backyard. The frontier of knowledge isn't always in the glaring unknown. It's in the subtle mismatch between what you predict and what actually happens, in that quiet, persistent tug on a machine that was built to drift free. The universe has this constant radio whisper, a faint background, but in 1977, for about 72 seconds, it shouted. An astronomer, Jerry Amon, he was looking at data from the Big Ear telescope. A printout of letters and numbers, and he saw this sequence, 6EQUJ5. He circled it in red pen, and underneath he wrote one word, wow. The signal was 30 times louder than the background noise. It was narrowband, focused on that one frequency, the frequency hydrogen emits, a frequency you'd think about for communication, and then it was gone. For decades after, they pointed every big dish at that spot in Sagittarius. It never came back, not once, so it's just this perfect spike, this one event. So what was it? There's a natural explanation: comets. A pair of comets were found later passing through that area. Their hydrogen clouds could, in theory, make that signal. But the timing doesn't work. Those comets weren't there in 1977, and no other comet has been linked to something that strong, that brief. Then you look at astrophysical events. A stellar flare or a star being torn apart, but those things usually leave other signs across other wavelengths. The WOW signal was clean, isolated. Then there's human origin, a secret satellite, space debris, but the signal's details and the way the telescope scanned the sky make a local source very hard to explain. It passed all the early tests for something not from here. This whole thing shows the basic problem. The universe is huge. Our window for listening is so small. A signal could be aimed at us for just a moment, and if our telescope isn't pointed at that exact spot, at that exact time, we miss it forever. The WOW signal could be that. A one-time event, a flashbulb going off in our direction for reasons we don't know. It teaches you something about humility and persistence, that the best clue might never come again. It makes you ask how you search for a needle in an ocean of noise, and it holds onto a quiet hope that maybe somewhere out there, something briefly pointed a transmitter at us. Whether it was a natural thing we don't understand or something else, the WOW signal is a monument to a moment when the cosmos seemed to speak, a single, unanswered hello across the light years. A mystery that isn't meant to be solved, maybe, just wondered at to keep us listening. The WOW signal was a flash, a one-time thing in the static, but there's another signal. A constant one, it's woven into space itself, a gravitational signature of something we can't see. So the final mystery in our solar system isn't a missing object. It's a missing substance, the nature of dark matter, right here in our own neighborhood. Most of the matter in the universe is dark. It doesn't emit light. It doesn't absorb or reflect it. We know it's there because of gravity. It pulls on galaxies. It shapes the cosmos on the largest scales. But what is it? And could it be here in a form we might detect? Models of our galaxy suggest the solar system moves through a diffuse halo of these particles. The sun's gravity, even the planet's gravity, might concentrate it a little. Create a slightly denser cloud around us, a ghostly halo right here in our backyard. The challenge is subtlety. If dark matter particles are here, they interact so weakly. Trillions could pass through your hand every second without a single collision. Detecting that whisper requires incredible precision. One approach looks at planetary orbits. If dark matter accumulates around the sun, its gravity could cause tiny deviations. In the path of Mercury or Mars, our tracking of spacecraft has become so precise. Cassini at Saturn, scientists can search for anomalies that small. A discrepancy of a few millimeters per second over years could be a clue. Other experiments aim for direct detection. Deep underground labs shielded from cosmic rays. Instruments waiting for the rare jolt of a dark matter particle striking a nucleus. But what if we looked in space? A dedicated detector in a stable orbit, far from Earth's interference. It could listen for this cosmic background. It would be like trying to hear a single snowflake land in a silent forest. Solving this would bridge two realms, the vast, abstract realm of cosmology and the intimate dynamics of our solar system. The same invisible substance that binds galaxies together could be gently tugging on the planets. It connects the fate of the universe to the path of a single spacecraft. This search reframes our home. We're not just on a planet orbiting a star, we're adrift in a sea of invisible matter. A sea that may hold the key to gravity, to mass, to the composition of everything. The quest to find dark matter locally is about curiosity. It's the attempt to touch the intangible, to measure the immeasurable right where we live. It asks if the greatest secret of the cosmos isn't in some distant quasar, but here, all around us, waiting for a sensitive enough instrument, a clever enough idea to reveal itself. The final frontier may not be a place, it may be a substance, and the solar system is our laboratory. These 25 mysteries, they aren't just scattered pieces, they connect. A solved puzzle on one world can light the path to an answer somewhere else. Venus, its missing magnetic field, that's not just a quirk of its core. It's a key reason its atmosphere turned into a crushing greenhouse, a stark contrast to Earth's protected sky. Our ocean water, delivered by ancient asteroids, that's a direct consequence of the late heavy bombardment. A period of violence, its record etched into the face of our moon. And that sharp cliff at the edge of the Kuiper Belt, that emptiness, it whispers of the great planetary migration, a gravitational dance that likely triggered that very bombardment. Each question is a thread in a single tapestry. Pull on one, and you feel the tension, the connection to several others. Understanding the faint, dusty rings of Jupiter teaches us about the processes that sustain the glorious ice rings of Saturn. Deciphering the chaotic terrain of Europa gives us a model for what might be happening under the ice of Enceladus. This is the true nature of the work. We aren't just making a list of oddities. We're detectives reconstructing a single, coherent story from 25 different crime scenes. Every mission, every telescope observation adds a sentence, a paragraph to this ongoing narrative. The Pioneer Anomaly taught us to account for every photon of our own spacecraft's heat. The search for methane on Mars forces us to refine our tools to detect the faintest whispers of chemistry. Each solved enigma doesn't just close a case, it sharpens our methods, it refines our questions, and it illuminates the neighboring mysteries in a new light. This systemic view, it transforms the solar system from a collection of separate worlds into a single, dynamic entity, a system with a shared history. Unimaginable collisions, graceful orbital dances, slow, relentless processes of change. The story is still being written. Every time a rover drills into Martian soil, or an orbiter maps the gravitational field of an asteroid, we're adding to the chronicle. We're learning to read the language of planetary science, a language written in crater scars, in atmospheric compositions, in orbital resonances. The ultimate mystery, then, may be the narrative itself. How all these individual threads, the spinning asteroids, the hidden oceans, the ghostly rings, the tilted giants, how they weave together into the story of our home. A story that began in a cloud of dust and fire over 4.5 billion years ago, and continues to unfold silently and magnificently all around us. Venus has scorching winds, the Kuiper Belt is a silent frontier. The solar system is full of wonder and complexity. It goes far beyond the simple diagrams. These 25 mysteries aren't just gaps in our knowledge, they're beacons. They're a reason to build a new telescope, to launch a daring probe, to refine a theory late at night. They pull us forward. There's a faint whisper of methane on a red desert, a geometric storm above a gas giant, a warm ocean under a shell of ice. These aren't puzzles to solve and file away. They're invitations to look deeper, to ask the next question. That constant curiosity is the engine of exploration. It turns data into stories. It turns anomalies into destinations. When a mystery gets resolved, like the Pioneer Anomaly, it doesn't end the quest. It sharpens our tools. It teaches us to look for the next subtle drift, the next tiny signal. And when a new enigma emerges, like that stark cliff in the Kuiper Belt, it redraws the map. it changes what we think is possible. Our cosmic neighborhood isn't a static museum. It's a living workshop, a place where the fundamental rules are being tested, the rules of physics, chemistry, planetary science. They're being rewritten before our eyes, so there's this tapestry of questions. Which thread pulls at your imagination the most? Is it the search for a hidden ocean's chemistry? Or the hunt for a missing planet's gravity? Is it the stark, two-faced moon, or the atmosphere that moves faster than the ground? Each mystery holds a different kind of key. A key to understanding our own world's past, its fragile balance, a key to imagining possibilities on worlds orbiting distant stars, and that's where the conversation continues. Share which of these 25 mysteries captivates you the most. Let's discuss what we might find when the next mission arrives at its target, when the next dataset arrives from the dark. If you've enjoyed this journey through our unsolved solar system, subscribe. Join us as we keep watching and listening and unraveling the secrets of our astonishing cosmic neighborhood. The next chapter is always being written.